Namaskar. The topic of discussion in this module is on physical oceanography. Oceanography is the scientific study of oceans and seas. It deals with the distribution of oceanic waters, marine resources, oceanic processes, dynamics of water masses, and the role of oceans on controlling the global climate. Oceanography encompasses four major elements as geological oceanography, physical oceanography, chemical oceanography, and biological oceanography. The physical oceanography is an essential part of ocean analysis. It is the study of physical conditions prevailing in oceans and also the large scale physical processes happening within the oceans. Oceans are very dynamic water bodies. The nature and role of oceans are continuously studied by the ecologists, geologists, marine biologists, meteorologists, and climatologists. A lot of oceanographic expeditions and explorations have been conducted by several groups of people under the support of kings and kingdoms. All those investigations have helped us to understand the oceans only to some extent. Still, there are a lot of things inside the oceans which are not known to us. Oceans offer a lot of marine resources, fisheries, mineral deposits, food and energy resources to the human population to survive. It is necessary for us to understand the integrated aspects of oceanography with all the available scientific facts, principles, findings, and observations. In this episode, the following aspects of physical oceanography are highlighted: the physical setting of oceans, ocean water properties, fluid mechanics and ocean dynamics, equations of motions with viscosity, waves, tides, and coastal processes. Let us see the first part of it, the physical setting of oceans. The earth has only one large marine water mass. It is distributed in the forms of seas, oceans, gulfs, straits, basins, and bays. The total volume of this mass is 1370 million cubic kilometers. It is higher than the volume of land above the sea level, which is only 130 million cubic kilometers. The total mass of the oceans is 1.5 into 10 to the power of 18 tons, which is 0.25% mass of the earth. There are five major oceans on the earth as the Pacific Ocean, the Atlantic Ocean, the Indian Ocean, the Arctic Ocean, and the Antarctic Oceans. All these water masses cover about 70.8% of the surface of the earth. The dimensions of oceans may range from 1500 kilometers to 13,000 kilometers along the latitude or longitude. The minimum width of 1500 kilometers is seen in the Atlantic Ocean along east-west direction, and it extends to more than 13,000 kilometers along its north-south extension. The surface area of the Pacific Ocean is 181.34 million square kilometers. Its average depth is 4,282 meters. The surface area of the Atlantic Ocean is 106.57 million square kilometers. Its average depth is 3,926 meters. The surface area of the Indian Ocean is 74.12 million square kilometers. Its average depth is 3,963 meters. The overall average depth of oceans is 3,800 meters. If we look at the depth regions throughout the oceans, we can see that majority of the area is occupied by the depth zone between 2000 and 6000 meters. But the deepest zones beyond 6000 meters depth are noticed only in a few places in the west and northwest Pacific, Midwest Atlantic, and a few isolated spots of the Indian and other oceans. The oceans are very thin layer of water masses when we consider them on a global scale. The vertical scale is very small when compared to the horizontal scale. Hence, for all graphical representations, the vertical scale is to be exaggerated. The ratio of depth to width of the ocean basins is also very small. This ratio is very important for understanding the ocean currents. The vertical velocities must be much smaller than the horizontal velocities. Very small amounts of vertical velocities may have a great influence on the water turbulence in these water bodies. Bathymetry is the mapping of ocean water column. It provides depth-wise relief features. The depth of the oceans are measured using acoustic echo sounders housed on ships and altimeters housed in satellites. Bathymetrically, the relief of the oceans is divided into three distinctive zones as continental shelf, continental slope and the deep ocean basins. All these three zones have unique physico-chemical and biological conditions. They are also characterized by distinct geological features and Earth's processes. The morphology and relief of the sea floor includes a wide variety of features. They include the submarine canyons, deep sea fans, abyssal hills, abyssal plains, mid-ocean ridges, deep sea trenches, sea mounds, rift valleys, ocean fractures, oceanic troughs and island arcs. Almost all these underwater features are under the influence of ocean water circulation, turbulence and also involve in interrupting the ocean currents as well. The Earth's crust is broken into various lithospheric plates that move relative to each other. There are convergent and divergent plate movements. Both of these movements are responsible to create new ocean floors at one side and subducting the ocean floors at the other side. Altogether, the relief of the oceans are under dynamic changes due to these continuing tectonic movements. Volcanic eruptions, earthquakes, rift valleys, rising of ridges, crushing of continental margin materials and tsunamis are expected during these processes. Let us see the very important concept of air-sea interface in the oceans. Air-sea interface is a very unique zone on the Earth. It is the zone which will have the maximum atmospheric influences. The atmospheric influences come due to the sun's radiant energy on one side and the wind-driven water movements at the other side. All dynamic processes in the oceans are directly or indirectly energy and also the atmosphere. The dominant mechanisms are the role of the sunlight, evaporation of seawater, infrared emissions from the sea surface and the cooling or warming of the oceanic waters. The atmospheric circulations are controlled by the oceans and the ocean water circulations are controlled by the atmosphere. Oceans are also the dominant sources and sinks of heat. Oceans can absorb, re-emit, store and transfer heat very effectively by its constituent water masses. The loss and gain of heat by the oceans produce winds in the atmosphere. Evaporation and condensation are two more mechanisms enacted by the heat in the oceans and also cooling in the atmosphere. Solar heating is an uneven energy source. This uneven heating controls the strength and directions of wind in the atmosphere. Due to this, high and low atmospheric pressure zones are also created. Warm and cold fronts are generated out of these changes. The atmosphere within 100 meters above the surface is influenced by the turbulent drag of the wind. This layer of atmosphere is called as the boundary layer. Wind measurements in seas and oceans have been made for several centuries. The world's oldest wind reports were made as early as 1855. Wind speeds were understood through a convenient system of reference as proposed by Sir F. Beaufort in the year 1806. This is called as the Beaufort wind scale. This scale is a graded level of denoting the force of the wind and its impact on water and also on the land. It helps to know the severity and intensity of the wind on the sea. The force level ranges from 0 to 12, representing the calm wind, to the hurricane on the water masses. Later, the state of the sea was also identified using the modified Beaufort wind scale as proposed by Kent and Taylor. Weather observations on ships, including the Beaufort wind force, are measured normally 4 times a day all over the world. They are done at 0 hours, 6 am, 12 noon and 6 pm at local times. Let us see the second part of ocean water properties. The sea water has certain physicochemical properties which play a very significant role in the hydrodynamics and also on the marine life. The notable properties of the sea water are the temperature, the salinity, the density and the light penetration. About 50% of the solar energy reaching the planet Earth is absorbed by the ocean and also by the land. 1/5 of the solar energy absorbed by the ocean is released back to the atmosphere through evaporation and infrared radiation. The balance is then transferred into the sea and is used for producing currents. The heat flux is the transfer of heat across the ocean and also along the sea surface. The flux of heat on water also changes the density of water and its buoyancy. It is estimated that about 4000 joules of energy is required to heat 1 kilogram of seawater by 1 degree centigrade. Insolation is the term denoting the incoming solar radiation. It is determined by latitude, season, time of the day and cloudiness. The polar regions are heated very less than the tropical regions. Areas in winter are heated less than the same area in summer. The heat in the morning time is less than the noon hours. There is no insolation at night. All these have an impact on the temperature of water in seas and oceans. Earth gains heat at the top of the tropical atmosphere and it loses heat at the top of the polar atmosphere. The north-south movement is called as meridional heat transport. The flow of heat, evaporation, rainfall, river water inflow, freezing and melting of the sea ice all control the distribution of temperature and salinity of the water in the oceans. Changes in these properties can increase or decrease the density of water at the surface. It also promotes convection. When the surface water sinks into the deep ocean, it creates much pressure variations and generate ocean currents. Warmest ocean water exists near the equator and the coldest water exists near the poles. The mean temperature of ocean water is 3.5 degrees centigrade. Next is the salinity of water in the oceans. Salinity is the total amount of dissolved solids present in seawater. It is represented as gram per kilogram of seawater. It is a dimensionless quantity. It ranges from 34.6 to 34.8 parts per thousand. It is also indirectly determined based on the conductivity and chlorinity of waters. Seawater contains higher concentrations of all cations and anions. However, sodium and chloride are the dominant species present in seawater. Conductivity and salinity are measured using conductivity meters. The mean salinity of oceanic water is found to be 34.7. The density of water at the sea surface is typically 1027 kg per meter cube of water. Changes in density generates vertical movement. Turbulence is the mixed layer mixes the heat downward. Below the mixed layer, the water temperature decreases rapidly with depth. Temperature and salinity measurements with reference to depth are done by using bathythermography, expendable bathythermography and also using Nansen bottles. Light penetration and absorption of light by oceanic waters are very important aspects for marine life to survive. Sunlight heats the seawater, warms the surface waters, provides the energy for all phytoplanktons and helps in the navigation of many marine animals. Let us see the third aspect, fluid mechanics and ocean dynamics. Ocean waters are subjected to internal and external forces. The fluid mechanics and hydrodynamics are the two major concepts underlying many processes and life support systems in marine environments. Fluid mechanics, Newtonian mechanics, conservation of mass, conservation of momentum, angular momentum and conservation of energy all are involved in the ocean water dynamics. The forces which are essential to understand the physical oceanographic processes are the gravity, friction and the Coriolis force. Forces are vector quantities. They have both magnitude and direction. Gravity is the dominant force. The weight of water in the ocean generates pressure. Due to solar lunar influences, tides, tidal currents and tidal mixing all happen in the oceanic waters regularly. Buoyancy is another parameter to be borne in mind. It is the upward or downward force arising due to gravity. It acts on the parcel of water. Density plays a catalytic role for enacting the buoyancy also. Horizontal pressure gradients are also created due to the varying weight of water in different parts of the oceans. Friction of wind blowing over the waves, force of water movement or air movement over water may create the frictional forces also. Wind stress is also created due to this motion. Ocean water circulation also includes origin and movements of waves and currents. The following are the types of circulation seen in the oceans. The general water circulation. This is a permanent time averaged circulation. The second one is the deep water circulation. This is driven by mixing in the deep ocean. The third one is the wind driven circulation. It is caused by local winds on the surface of the oceans. The fourth one are the gyres. These are wind driven cyclonic or anticyclonic currents of giant magnitude. The fifth one belong to the boundary currents. These are currents flowing parallel to the coast. The sixth one relates to the jet streams or the squids. These are long narrow currents with dimensions of few hundred kilometers perpendicular to the west coast. The seventh one relates to the mesoscale eddies. These are turbulent or spinning floats running for a few kilometers in the ocean waters. The other essential part of study in physical oceanography is the conservation of mass and salt. These help in deriving the continuity equation and also for understanding the dynamics of mass and forces in waters. The next part is related to the equations of motion with viscosity. The role of friction in fluid flows and the stability of the flows to small changes in velocity or density are to be understood in physical oceanography. Viscosity is the tendency of a fluid to resist shear. The influence of viscosity, especially the molecular viscosity, which comes due to striking of water with solid mass, is to be analyzed. The components of stress at a point in a fluid having pressure include normal stress, and the other one is called as shear stress. In oceanic waters, stability is yet another parameter to be understood. Many kinds of instability occur in these water masses. The kinds of stability to be understood are static stability, dynamic stability and double diffusion stability. Static stability is associated with the change of density with reference to depth. The dynamic stability is associated with velocity shear, and double diffusion stability is associated with salinity and temperature gradients in the oceans. Steady winds blowing on the sea surface produce a thin horizontal boundary layer called Ekman layer. This layer may be a few hundred meters in thickness. Ekman layer transports water at right angles to the wind direction and subsequently generate upwelling. This upwelling enhances the biological productivity to feed the fishes and other marine life. There is also a deep ocean Ekman layer near the ocean floor. A current that spirals around an axis parallel to the direction of the wind is called as Langmuir circulation. It is customary to think that ocean currents are driven mainly by the winds. Currents and ocean circulations are driven by not only the winds but also the other factors and forces caused by the site, location and space on the globe. The role of geostrophic currents is yet another mechanism in physical oceanography. The theory for wind-driven geostrophic currents was studied by the scientists Sverdrup, Stommel and Munk between 1947 and 1951. Satellite altimetric observations of the ocean topography can give the time-variant data of surface geostrophic currents. Hydrographic data are also used to calculate the internal geostrophic currents in the oceans. Flow in the ocean that is independent of depth is called as barotrophic flow, and the flow that depends on the depth is called as baroclinic flow. Baroclinic flow can be determined by using hydrographic data. There are several types of ocean currents existing in the oceans. They are the Antarctic circumpolar currents, deep ocean density driven currents, western boundary currents which include Gulf Stream, Kuroshio current, Labrador current, Oyashio current, Agulhas current, Brazil current, East Australian current, and the eastern boundary currents include California current, Canary current, Peru current and the Bangulia current. In the oceanic waters, rotations and the conservation of vorticity strongly influence the flow over distances exceeding a few tens of kilometers. Vorticity is the rotation of the fluid. There are two types of vorticity as planetary vorticity and relative vorticity existing on waters. The sum of these two is known as the absolute vorticity. Vorticity strongly influences ocean dynamics. The curl of the wind stress adds relative vorticity to the central gyres of each ocean basin. The deep circulation in the ocean is also an aspect to be understood. The equatorial currents moderate the air-sea interactions through the phenomena known as El Nino. It is an acronym for the child Jesus. These are found to be counter currents existing along the Peruvian coast. The east-west temperature gradient on the equator drives a zonal circulation in the atmosphere. This is called as Walker circulation. El Nino denotes a disruption of this entire equatorial system along the Pacific. It causes changing weather patterns around the globe. The term El Nino is related to the southern oscillation called ENSO. El Nino is a sea level pressure anomaly in the eastern equatorial Pacific region. The tropical and equatorial Pacific is a vast ocean. It is a remote area which is seldom visited by the ships. El Nino causes the biggest changes in the equatorial dynamics. During El Nino, trade winds weaken in the western Pacific. This generates the Kelvin wave eastward along the equator. These are the largest sources of annual fluctuations in the global weather patterns. Due to this, drought occurs in the Indonesian area and also northern Australia. Similarly, floods occur in the western tropical South America. Let us see the waves, tides and coastal processes. Ocean waves are powerful systems shaping and reshaping the coastal zones. Waves have enormous energy. When we look at the sea from the above, we can see thousands of waves on the sea surface approaching the coast. These are undulations of the sea surface with a height of around a meter or few meters. Each wave has a wave height which is the vertical distance between the bottom trough to the top crest of the wave. The wave length is the distance between two prominent adjacent crests or troughs. The wavelength may range from 50 to 100 meters. When we watch these waves for a few minutes, we can notice that the wave heights and wave lengths are not constant. They vary in space and time. Wave period is the time taken by two successive waves to pass through a fixed point. All offshore waves are generated by the wind. It is also true that the sea level changes from hour to hour. Sea level increases and decreases during a day. The slow rise or fall of the sea level is due to the tides. Tides have wavelengths of thousands of kilometers. They are generated by the slow, very small changes in gravity as influenced by the moon and also the motions of the sun. In physical oceanography, a detailed study of the ocean waves, tides and their impact on the coastal zones is needed. Waves are the natural and outstanding phenomena of the oceans. Wave phenomena involve the transmission of energy and momentum by means of vibratory impulses. Observations by mariners on ships and satellites using sensors and altimeters help to prepare the global charts and maps of the wavelengths. In addition to the wave heights and movements, the directions are also detected by the modern sensors. In addition to this, it is also necessary to understand the coastal processes and the tides. Waves break if the water is sufficiently shallow. The broken waves pour water into the surf zone, creating longshore and rip currents. Rip currents are dangerous things for the swimmers. Edge waves are produced by the variability of wave energy reaching the shore. Tsunamis are yet another issues in oceans and coastal regions. The impact of tsunamis are very devastating. The recent tsunamis have made the whole world population to think very seriously about the natural disasters. Tsunamis are low frequency ocean waves generated by underwater earthquakes. They are also called as seismic sea waves. Sudden motion of seafloor over distances of 100 or more kilometers generated tsunamis with wave periods of 15 to 40 minutes. These may propagate at a speed of 180 meters per second with a wavelength of 130 kilometers in water. Tsunamis may be 3.6 kilometers deep and is not noticeable at the sea surface. After nearing the coast, the surge may rise up to 10 or more meters above the sea level. A tsunami can travel thousands of kilometers and do serious damages. The first wave of a tsunami is not likely to be the biggest. Many a time, storm surges also play a very unique role. Storms blowing over the shallow continental shelf regions pile water against the coast. The increase in the sea level due to this pile-up is known as the storm surge. Oceanic tides produce strong currents in many parts of the ocean. Their speed may go up to 5 meters per second in the coastal waters. Oceanic tides have a great energy. They modify the coastal geomorphic conditions very often. Shorelines of submergence and shorelines of emergence are two important aspects related to these waves and tides. Coastal erosion, coastal sedimentation and tidal inflow are all the natural effects of these processes. The study of physical oceanography helps in understanding all these aspects in detail. Let us see most of these factors and processes in our future modules. Thank you.